Hi, good evening. So, shall we start, Neeraj?
Yes, sir.
Okay. So, this week just was about DC series machine, right? So, we will look the problems that were given. Yeah. So, let's take the problem. So, I hope you are aware with the all basic concepts of DC series machine, right? So,
Yes,
we can clarify also. I hope my screen is visible.
yes, sir.
Okay. Thanks. Yeah. So, this is the first problem. Okay. Here, a 250 volt DC series motor has armature resistance of 0.5 ohm and field resistance also is equal to zero point 0.5 ohm. And it is running at 800 RPM while drawing 20 amps of current. And if you are aware with the DC series machine's equivalent circuit, you might be knowing that armature resistance and field resistance. So whatever armature current will flow in the circuit, that will be equivalent to field current of the circuit, right? So it is the supply voltage and it will be your back EMF, and this you can consider as RF and RA. Okay. So another condition is given that load torque is constant and magnetization curve is linear. Now, it's fine till now. Then a 0.5 ohm of diverter is connected in parallel with the series field. Okay, so what's the purpose of providing a diverter? If you could guess here, it's just to,
Reduce the field
to
current, sir.
uh, not produce the field current because anyway, if
Reduce.
you have, okay, reduce, yes, yes, yes. So that's exactly, you could reduce the field current, and so by that means you are indirectly weakening your field flux, and you can go at higher speed with rated voltage. Okay, so earlier our current was let's say 20 ampere. Now the current will be traveling how much in both the paths, that we have to find out, and in the question we have to find out the new speed. Okay, so what will be the speed after 0.4 0.5 ohm diverter is connected, and the initial speed was 800 rpm is anyway given. So let us find out the speed. So what should be our approach here? So again, when speed is concerned, then we have to go directly to the back EMF thing. So first thing we should find out for case 1, EB1, we can find out from VT minus IARA. IA was 20 and RA was 0.5 and RF was also zero point 0.5. Since if you can apply KVL in the circuit, right, so it will provide you something 230 volt if I am not wrong. So this is your EB1. Now at this back EMF we have 800 RPM. Okay. If I need to find out when one extra field resistance with the same amplitude is connected, then how much current will flow, so that we can calculate back EMF. Okay. How much IA2 is flowing. Okay, this was for case 1. Now how much IA2 is flowing so that we can calculate EB2. Okay, so IA2. Yeah.
Hello.
Yes.
Sir, your voice was not going for a while.
Oh, so was I not audible? From
So
which
there
point,
is.
if you could let me know, and if now whether am I audible or not?
Yes, sir. I can hear you now, sir.
Okay, now you can hear me. Let me check the internet. I guess it is by default on this network. Mm, Please confirm once whether am I audible or not.
Yes, sir. I can hear you, sir.
Okay, okay. So could you please let me know from which point you lost me?
Sir, when you have explaining the EB1 calculation, sir, after that, when you
Okay,
started to write IA2,
okay, okay. Yeah.
your
So
voice was lost.
after this line, right?
Yes, sir.
Okay. So I was mentioning that we have to calculate EB2 such that we can calculate the naval speed, right? And to calculate EB2, we must know the value of IA2, right?
Yes,
In
sir.
that condition, only we will be able to calculate EB2. Okay.
Yes, sir.
So I was asking that how to go ahead to find out the IA2. Right? So
So
yeah.
we can use that condition that low torque is constant.
Yes.
Then,
Great.
then the product of phi and IA will be
Uh-huh.
constant, sir, in both the
Yes.
cases.
Great.
But
Yeah.
due to applying the diverter, field is getting reduced by
Yes.
some fraction. By the same fraction, IA should increase for the second case, sir.
Yes, yes, exactly. So what will we do? We will equate phi 1 into IA1 is equal to phi 2 into IA2. Okay, so phi 1 we can take as a reference. Phi 1 we can take as phi. Now, because of diverter and both have the equal resistance, so current will flow equally in both the branches, right? And
Yes, sir.
both the current will come here from the KCL and it will be same IF. So here, if this is IF2, this will be IF2 by 2, and here also it will be IF2 by 2. So, and from if we this condition is given that magnetization curve is linear, so we can directly say that phi is directly proportional to IF, right? So phi 1 we can write it as K1 into IF, and phi 2 also we can write K2, sorry, K1 into, from this logic, K1 into IF by 2. So which will be what? Phi 1 by 2. Okay. So if you plug in those values here, you will get IA2 is equal to mm, 0.5, so 2 IA1. Okay.
So 40.
So it will be 40 amps. So we are done with the current calculation. So next step is that we should find out the EB2, and after that we are good to compute our speed. So EB2 we can calculate, that will be Vs minus IF by 2, right? Or let's suppose IF by 2, right? And in second case, since let me indicate it here. So since here it is flowing 40 amps, here it will be 20 amps and 20 amps. So if you apply KVL, okay, yeah, one resistance is there. So it will be 20 into RF 0.5 minus 40 into RA. RA is again 0.5 and VS is anyway 230. Sorry, 250, I guess. So this equation will lead to 240 minus 20 minus 10. So it will be 230 volt. Sorry, 220 volt. So we are done with EB2 calculation. Now we cannot just straight away equate EB2 by EB1 is equal to N2 by N1. We have another component also, phi 2 by phi 1. And phi 2 by phi 1 we know is equal to 0.5. In second case, flux is reduced by 50%. So now we are good to calculate EB2 by EB1. Right?
Yes, sir.
Yeah. So it will lead to N2 by N1 is equal to EB2 by EB1. EB2 is 220. EB1 was 230 and divided by 0.5, so 2. So how much it will give us?
1.913.
1.913. So from this logic, N2 will be 1.913 times 800, right? So how much it will be?
1530.
1530 RPM. Okay. So I hope it is fine, but feeling, did we commit any mistake in this problem? No, I guess we did fine, right? So
Yes,
let
sir.
us summarize again that since phi 1 into IA1 is equal to phi 2 into IA2, so yeah, we are good. Okay. So any doubt in this? I think it is fine.
Yes, sir, it's
Next,
fine.
and yeah, in this problem also we needed to compute the armature current. So armature current in second case already we have found, that is 40 ampere. So in whenever we deal with DC series motor, this field current and armature current is always coupled. Both are coupled to each other. So you cannot independently change the flux, and you can tweak your armature currents to get the desirable torque at desirable speed, which is quite possible in shunt machine and other machines. So that's another thing that in DC machine it's a bit undesirable. Like you cannot have separate control for two different entities. So whenever you are trying to change your output, but you do not have control on the flux in the machine. So flux will come in the picture every time you change the armature current. That's why its characteristics is bit different from all the other machines. Okay, so let us go ahead with the next problem. Yeah, so in this question also, we have a DC series motor with 0.5 ohm of resistance, and it is driving a fan Okay, so it is driving a fan at 500 rpm. So basically, this kind of motor is very much suitable to drive the fan kind of load. That's why every time you see a question related to DC series motor, it's always associated with fan type of load, and torque is directly proportional to a square of the speed. Okay, so when the speed increases, your torque also increases, and you can see this characteristics as something like this. So this is a typical characteristics. As you go at higher speed, you can achieve higher torque, which is not available in other characteristics, because as you are trying to increase the flux, you are also trying to increase the current, and your torque will increase. So hence, this kind of characteristics, torque is proportional to a speed square. Also, torque is proportional to Ia square. Okay, why I am saying torque is proportional to Ia square? Because just now in the last problem we seen that torque is equal to K phi into Ia, and phi is again proportional to Ia for linear reason, right? In saturation, it will be K phi K times Ia. Once your machine is saturated, then flux you cannot vary above the rated flux, right? It will take so high current to surpass that value, but current can increase. So mm, below base speed, below base speed or below rated condition, you can vary torque is proportional to Ia square, but above base speed, your torque will be more or less proportional to Ia. Okay, so in this problem, it is given the condition that load torque is proportional to the square of the speed. We have to change the speed of the motor to 600 RPM by controlling the supply voltage. Okay, so you have the control only on the supply voltage. Now, again, we have to assume linear magnetic circuit, which means we can ignore the saturation criteria of the machine, and we have to estimate the required supply voltage. Okay, what what value of the voltage you can apply at the terminal, so that you can change the speed from 500 rpm to 600 rpm. Hmm. So any
Hello,
approach
sir.
coming in your mind? Yeah, go ahead, Deepak.
Sir, we did study that the torque is inversely proportional to speed, but here is a directly proportional. Why?
Yeah, so see, you have studied torque is proportional to inversely proportional to a speed, right? You have studied this, but when
Yes, sir.
this is provided when your power is constant. Okay, and when your power is constant, then only you can say that power is equal to torque into speed. And when it is a constant, then torque will be inversely proportional to speed, right? It will not be always true. Okay.
Okay.
Okay. And when you come to DC machine, DC series motor characteristics, okay, at lower the speed, what will happen? At lower the speed, the characteristics is proportional. That is the characteristics of that load it is driving. So what happened at lower speed? You tell me. Let's say it is omega 1, it is omega 2. This is the speed, this is torque.
The power is constant here, and so torque will be high.
Mm, no. Uh, See, at lower the speed, what happens? If you let me derive it, okay, for you. So if you write it as Vt is equal to Eb minus Ia Ra plus Rf. Okay. Now, Eb is what? Eb is K phi omega. Okay. Minus Ia. Ia we can write it as torque divided by K phi, right, into RA plus RF. Do you agree till now? Now we want to find out the relationship between torque and speed. Okay. And phi is directly proportional to IF. So we can write it as, let me bring the torque component left hand side, divided by K into IF. At phi we can write K1 as IF is equal to K IF into omega minus Vt. Okay. So I hope you are getting where it is going. Right now, if you equate it, you will get K omega IF into IF K1 divided by RA plus RF minus Vt into K1 IF divided by RA plus RF. Okay, so it is kind of characteristics, and if you equate it further, K omega IF square divided by RA plus RF minus VT K1 by RA RF into IF. And IF can be equated to IA, right? Because it is a series machine. And you can see that as speed will increase, right? As speed will increase, what will happen to the field current? So initially, what kind of field current you want to provide? At very starting, let's suppose at omega is equal to 0, this torque will be huge. That's the characteristics. If you, I think I'm missing some term here, but mm, generally one omega is comes in the denominator, some omega square kind of term. So let me into IF into IA and IF we can write it as I, and EMF is equal to K phi omega. So phi is equal to E by K omega. Okay. Yeah. So from this expression, right, at the place of IF, this is a separate thing. Okay. We can use this expression here, and this omega square was not earlier present. Earlier IF was present only. So IF square was here, right? Uh, I hope you are not getting confused. This term IF square is here, right?
Yes, sir. But
Yeah.
this K1 are different. K and K1 are different to each other.
Yeah. Yes, they are different. They are different in what term? They are different in terms of phi is equal to K1 IF. Phi is equal to K1 IF, and K is the constant which comes in the speed and back EMF relationship, right? So this IF, or if you mean like IF, let's clarify it. You mean that I have taken K1 as what? Phi F is equal to K1 IF, right? So now, mm, okay. let's here it was K5 and here also it was K5. Okay, fine. Till now it is fine, right? Now
Yes,
what
sir.
I am going now what I am going to plug in here at the place of phi is equal to EB by Q omega. Okay, you agree? This expression you can recall, right?
Yes, sir.
Yeah. Now further torque we can write it as K square phi square omega divided by RA plus RF minus VT into K phi divided by RA plus RF. Now we want in terms of a speed only. We want variables in terms of a speed. Okay, we want other things constant. If you want to visualize how the variation will go on with the variation of a speed, we should make all the other terms constant. That's the way to derive, right? So how will you make other terms constant? Because phi is also variable here. Okay. So what we will do, we will plug in this value of phi in this expression and here as well. So you will end up with omega Ra plus Rf, and phi is nothing but EB square divided by K square omega square minus Vt into K phi nothing but EB by Ra plus Rf into K omega. So this K and this K will be cancelled, and this K square and this K square will be cancelled, and we will end up with EB square divided by Ra plus Rf into 1 by omega minus Vt into Eb by Ra plus Rf, again 1 by omega. So you can add both the expressions, so you will end up with Eb square divided by Ra plus Rf. Sorry, Eb we can take common, so Eb minus Vt, okay, into 1 by omega. Yeah, so here torque is indirectly proportional to speed, so that's why it comes at when your speed is zero, at that time your torque can become infinite. So that's why a starting torque is very high in the DC motor. So you were referring to this term only, right?
Yes, sir.
So are you convinced from this derivation?
Sir, in DC motor, we cannot on without any load due to
Yeah, yeah,
this highest torque.
yes. Because of very high starting torque, we do not generally start at no load. That's the reason behind it. So we should have certain load so that some current is there. And as you increase current, your starting torque will come down. As you increase current, so the another derivation will be there, which is given in many textbooks. So you can refer. What happens when you plug in some, you compare between no load and loaded condition. So here itself, if you can relate, you what you do, you play with this equation. Okay, at no load, this component will be gone, right? So when this component will be gone, you will have Vt is equal to Eb, which will be k phi omega. And another thing is that uh, torque you can anytime equate, but torque you can get it as k phi Ia, but initially both are zero. I think okay, we should avoid this expression. So what happens initially that a speed and flux you can vary. So from this expression, I think you will end up with certain another thing. I don't remember that exact derivation, but you can find them in the textbook. Or you can solve some problem. We will be solving some problem based on that, so that we will get some idea of it.
Yes, sir.
Okay, so coming back to the problem, that we needed to change the speed from 500 rpm to 600 rpm by controlling the supply voltage. Okay, so for that we need back EMF, and then we can apply the KVL and KCL. Yeah, so again we have to find out the EB1, right? So EB1 can be calculated as 230 volt supply minus IA is given 25 ampere, RA is 0.5, and this is the motor has 0.5. Okay, so it means that Ra plus Rf will be 0.5 because nothing is given about separately field resistance and armature resistance, so we have to go with only 0.5. So total resistance is 0.5. Now it will give us something 217.5 volt at 500 rpm. At this time we require 230 volt. Okay, now at 600 rpm, what we can do, EB2 by EB1 is equal to phi 2 by phi 1 into N2 by N1. Now phi 2 will be proportional to armature current. So again, we have to find out the armature current in the second case. And for that, we are given that torque is proportional to speed square. So T1 by T2 we can do equal to N1 square divided by N2 square into, not into, is again further phi 1 into IA1 divided by phi 2 into IA2. Okay, so nothing about torque is related to torque and the speed relationship. This relationship was provided, and this is a universal relationship between torque and current. So what we can do, we know N1 by N2, right? 5 by 6 square divided by phi 1 by phi 2, or phi 1 by phi 2 is what? IA1 by IA2, right? Phi 1 is equal to IA1, we can say, when we are equating in terms of proportionality, so that we can directly write it as IA1 square divided by IA2 square. So which will give us IA1 by IA2 is equal to N1 by N2 which will be further equivalent to, we want to find IA2 N2 by N1 into IA1. So N2 is 600 divided by 500 into IA1 is 25. So IA2 we ended up finding out 30 amps. Okay, so now we can calculate EB2, VT minus IA2 into R, which is equivalently to RA plus RF. So VT is 230 minus 30 into 0.5, which will be 215 volt. Okay. So is it fine? EB2, no. So yeah, I guess it is fine. Now after that, if you are done with EB2, then what you can do is you can calculate the supply voltage, which will be equal to EB2 plus IA2 into R. So EB2 is 215 plus IA2 is 30 into R is 0.5. So it should not lead to again similar value, right? Some
Sir,
mistake
in
is,
this question we are changing the V, sir. Uh, But
yeah.
for
So
calculating EB2, we have taken V to be 230.
yes, yes, yes. So this is not the correct way to calculate EB2. Yeah, yeah, you got it right. So when we are assuming that VT is same, then there is no point of calculating that. So the approach is what? Another approach is EB2 by EB1, right? So EB2 by EB1 is nothing but, here we did IA2 by IA1, we can write into N2 by N1. So from this, EB2 and EB1 we computed to 17.5 is equal to IA2 is 30 amps, IA1 was 25, into N2 was 500, sorry, N2 is 600 and N1 was 500. Yeah, so now I think EB2 will be correct value. So how much it will be? 6 by 5 into 6 by 5 into 217.5 is equal to 313.2 volt. Okay, so it is higher than that. How come? Okay, anyway, if back EMF has been increased from, uh, it has exceeded from the supply voltage. Okay, so that's why we need to apply the new supply voltage, which should be much higher than this back EMF, right? At least it
Yes.
should be higher than this back EMF. So for this back EMF, we will have EB2 plus IA2 into R, and it will be 313.2 plus IA2 is 30 into 0.5. So it will be equal to 15, 13, 28, 328.2. So now this much voltage we need to apply. If if we have only control on the voltage, okay. So this much amount of voltage we need to apply, right? So yeah, we have always the tendency to consider the supply voltage constant, but it will vary if we do not have any other control on any other parameter, right? Any final doubt in this problem?
No, sir.
Okay. And this required voltage was when the circuit is linear. Okay, so we have assumed in this problem that we had linear magnetic circuit. Now what will happen if we remove the linearity and we have to consider the practical scenario, which means we have to consider that saturated saturation we have to take in the account. Okay, so in saturation what will happen for the same problem, what will be the supply voltage that we will be end up applying when we have certain saturation in the circuit? So
What, sir?
uh, didn't you get the problem statement? So we found out the supply voltage when
Okay.
we assume that our magnetic circuit is linear, which means the flux will increase proportional to the field current, right? In the last problem, we straight away put phi is equal to if, right? But now we cannot do that. We cannot do that phi is equal to if. Rather, above rated speed, we have to consider non-linearity of the magnetic circuit.
And now we want to calculate VS, supply voltage.
Yeah, now again we need to calculate the Vs and what will change. So that we will see. Okay. So let me bring that problem again. Okay. So this condition is changed. This is not anymore valid. So again, we have to find out the back EMF, that's for sure, because we have to calculate the voltage. So first we must calculate the back EMF for the new case. So back EMF for the initial case was we have calculated EB1 is equal to 217.5 volt at 500 RPM. Now EB2 at 600 RPM will be how much? Okay, for that EB2 by EB1 is equal to N2 by N1 into phi 2 by phi 1. Now, what will be the relationship between phi 2 by phi 1? Can we write phi 2 by phi 1 is equal to IA2 by IA1?
No, sir.
No, it is not valid anymore. Why? Why it is not valid anymore?
Sir, because the material has reached saturation, and even if we increase IA, the phi will not increase. It will remain at the same.
Yes, yes, yes. Your IA2 value may change, but phi 2 will not change. Okay, so for that purpose, we have we are concerned with flux only. So above rated value, it's very difficult to change them, right? So what will happen that uh, we can calculate it from the torque equation how much current will change. But anyway, we have understood that we are increasing it from the rated speed, which was 500 rpm, to newer speed. So our flux will be, for sure it will be constant, because it has already reached at saturation at rated condition. So phi 2 by phi 1 will be constant. Now from the torque condition, T2 by T1 is equal to N2 by N1 square into IF2 by IF1, right? So, and IF2 by IF1 again will be removed because they were constant, as we seen here. Now they have again another expression, K phi IA, right? K phi IA. So phi 2 into IA2 divided by phi 1 into IA1. Again, they are constant, so we have to remove them from the picture. So now IA2 by IA1 is equal to N2 by N1 square. So that is why our IA2 will be equal to IA1 was how much? 25 amps into 6 by 5 square. So it will be 36 amps. Okay, so we got IA2 value. Now, what will be the EB2 by EB1? EB2 by EB1 will again be straightforward. EB2 will be equal to EB1, that was 217.5 into 6 by 5. Okay. Now it will give us how much? 217.5 into 6 by 5. It will be 261 volt. So EB2 also we have 261 volt, and IA2 we again have. So we can calculate here VS2, which is EB2 261 plus 36 into 0.5. So this will be our new supply voltage at this speed. So it is 18, so 279 volts. So when you assume non-linearity, which is the practical condition of the machine, you will end up with this much voltage, 279 volt, instead of, in earlier case, we ended up with 328.2 volts. So here your field is not varying above the base speed because of the obvious reason. You have saturation in the machine, so above base speed, it will be difficult to vary or increase the flux, and that's so even for this sort of current. Any doubt in this?
Sir,
Huh.
how did you write this T2 by T1 is equal to N2 by N1?
A square, right? N2 by N1 a square.
Yes, sir.
It was provided in the problem, right? Low torque is
Okay.
proportional to square of the speed.
Okay. And sir, how you can say that 500 RPM is the rated speed of the fan?
Because at rated condition, it is given. These are the rated conditions at 230 volt of supply, 25 amperes of current, 500 RPM. It is the rated condition provided, right?
Yes,
At
sir.
which you have the rated flux. Now you are increasing the speed. So what will happen?
It's
That
increasing the speed.
hmm,
We have to increase the supply voltage.
You have to increase the supply voltage, obviously, because you do not have any control on flux separately. Because if you are going to change the flux, then you will end up changing your load torque or current, right? So that's why you cannot manipulate the field current separately. So now, to operate at the load torque, which requirement is itself is the square of a speed, okay, that you have to maintain from supply only. Is it fine?
Yes, sir.
Hmm. Okay. So yeah, so the new current is, again, we drawn the new current that is 36 ampere, and at this current your field will also change, but field will change, but it does not imply that your flux will also change. So your flux is now almost same, almost equivalent to whatever was at rated condition. So okay, let us move ahead with the next problem. Okay, so I will be back in a minute. Just read the question in there. Yes, you have read the problem. So any approach you are able to suggest? Okay, so let me read the problem once more. A 110 volt 8 pole DC series motor has 8 field coils connected in series. It was drawing 30 amps of current and driving a fan load at 500 RPM. The load torque is proportional to a square of the speed. The magnetization curve is linear. So again, we can ignore the saturation condition, and all losses you can also ignore. Now, in the next case, you are reconnecting the 8 field coils in two groups of 4 coils in series. So This last statement is apparently what they are saying, that they are reducing the field current, which means field flux. Okay, so again, we have to estimate the new speed, which means we have to again end up with some new back EMF. And again, we will go ahead with EB1 and EB2. So EB1, we can calculate. So as I mentioned in the last problem also, that load torque will be generally proportional to the square of the speed for such kind of motor. And for that, EB1, we can find out that 110 minus 30 amps into RA. What is RA here? So
Zero, sir.
RA 0. Okay, how
Sir, all
come?
losses are negligible.
Okay, so all losses are negligible. So IA square RA plus RF will be 0. So 0, so it will be 110 volt.
Sir,
Hmm.
where are you writing? We are not able to see.
Not able to see. Are you able to see, Neeraj?
Yes, sir, I can see that.
So what you do, Neeraj, you can just leave this and rejoin.
Sir, I can see that. Deepak has to rejoin, sir.
I'm telling Deepak. Did I say Neeraj?
Yes, sir.
Okay, sorry. So Deepak, you rejoin the meeting. Okay. So yeah, new speed will be N2, and that time current we can assume IA2. Okay, okay. So, but are they RF are 0? But they cannot be 0 because they are provided with some field. Okay, anyway. So has he joined? Deepak has joined.
Yes, sir, I have joined.
Oh, okay. Now you are able to see the screen, right?
Yes, sir.
Okay. So it's for sure that IF2 will be IA2 by 2. Okay. And this old flux and new flux will be, let me write it as EB2 by EB1 is equal to phi2 by phi1 into N2 by N1. Now, in such case, N2 we don't know, phi2 by phi1 we know, phi2 by phi1,
Sir,
phi2 is equal to, yeah, go ahead, KIA2.
sir, in this case, IF2 is not IA2 is not dividing in two parts because we are connecting force in series in two group of parallel.
Yes,
So
yes.
IF2 is not equal to IA2 by 2.
Why? So, what should it be?
Sir, I am not able to calculate, but I think they are not equally divided because three coils are in parallel.
Three coils are in parallel. Three coils are in parallel. How you can conclude that three coils are in parallel? See, two parallel groups only. Initially, what was the scenario? That 8 such coils were in series. Right? Now, what we are doing, we are breaking this and we are connecting them in two parallel group, right? So what will happen in such case? And this is further connected to your armature resistance. Here also it will be further connected to armature resistance and back EMF and all, isn't it? Whatever IA2 will go, since both are equally IA2 by 2 and IA2 by 2. Don't you agree with this?
We are connecting in this manner means we are not connecting externally another coil.
No, we are just reconnecting. The 8 field coils are reconnected in two parallel groups of 4 in series. You can read this statement carefully.
Okay, sir. I got it. I get it.
Okay. Yeah. So EB1 was 110 and EB2, by EB1 we ended up finding this. And since Neeraj has already pointed out that we have been given with very useful data that all the losses are negligible, which means EB1 will be equal to EB2. How I am saying this, Neeraj? Oh, sorry, Deepak. How I am saying this? EB1 is equal to EB2.
Losses are negligible means there is no resistance.
Yeah, whatever will be current, IA2, that multiplied with 0, it will be 0. So this is one. Now we can say that phi 2 by phi 1 is equal to N1 by N2. And phi 2 is nothing but I2 by I1 is equal to N1 by N2. Okay, so till now we are good, but
Sir,
we
here I
don't.
think we should write IF2 and IF1. Sir.
Yes. IF2, yeah, see, if even if we write IF2 and IF1, but indirectly, what will they become? Okay,
No,
you have made a very good point. Yeah. So IF2 by IF1, and yeah, further we can simplify IF2 is equal to IA2 by 2, right? And IF1 is equal to IA1. Yeah, here the scenario will change. So now IA2 by IA1 is equal to 2N1 by N2. Mm-hmm. So now we are not aware with IA2. We are not. We have to find out this N2. We have N1. We have IA1, right? So how to find two unknown variables? Any condition is given. Let us revisit the problem. Torque is proportional to square of the speed. Okay. So torque is proportional to square of the speed. We can write T2 by T1 is equal to N2 by N1 square, and further T2 is equal to T2 by T1 is equal to phi 2 by phi 1 into IA2 by IA1, and phi 2 by phi 1, which is equivalent to IF2 by IF1, which is again equivalent to IA2 by 2 IA1. So let me plug in into 1 by 2. Hmm. So one equation we had here, which we plugged in and we got this. So here we will get IA2 in terms of a speed N2 by N1 into I1 by root 2. Okay, so IA2 by IA1, we get the two different conditions. Okay, no problem. Load torque is equal to, yeah. So, but these both are same equation, right? IA2 by IA1 and N1 by N2. We ended up with different values. So what we do, we just plug in here IA2 by IA2 into N2 is equal to 2N1 IA1. So 2 into N1 is 500 into IA1 is how much? IA1 was 25. So 25, isn't it? No, 30 amps. IA2 is 30 amps. So it will be 30,000. Okay, now we equated it here. Hmm. Uh, They are looking similar, but they are not exactly similar. See, I thought that both the expressions are same. Are you able to point out the difference between these two? Let me zoom out, zoom it.
Their root 2 terms should be in the numerator, sir, isn't it?
Where? Here?
Last equation, sir.
Yeah, yeah.
Root 2
Here
term
root.
should be in the numerator.
Yeah, that it is along with I. Yeah, that's correct. That is fine. But apart from this, any other difference you are able to find out with these two? Mm, okay. Okay, let me bring back this part.
Sir, does is the torque changing here, sir? Or is it just
Actually, actually, if we see carefully, these two expressions are different. Okay, let me bring back both of them side by side, then we will be able to figure it out clearly. It is here IA2 by IA1 is equal to 2N1 by N2, okay? And here IA2 by IA1 is equal to root 2 N2 by N1. I thought that both are identical and why we are getting same values, but both are not identical. This is coming from one condition. The condition above was like torque is directly proportional to speed square, and here we got it from this, right? One is
sir? I
one
have one idea,
condition. Yeah,
sir. Let's write both those equations in terms of IA2 and then equate those two. Then IA2 term will be gone.
yeah, yeah.
Then only unknown will be, sir, N2. N1 we know that, sir. IA1 we
Mm,
know.
yeah, definitely. So, from first condition we got N2 IA2 is equal to 30,000, and if here, like from this condition, if here we can manipulate in that manner, IA2 and divided by N2 here, right? IA2 by N2 is equal to root 2 into N1 by IA1. N1 was 500, IA1 was 30. So it is different than this. That's what I wanted to point out, that from the first condition, when our back EMF was, the ratio of back EMFs were 1, which means losses were negligible. From that condition, we got this equation IA2 by IA1 is equal to 2N1 by N2, which gave us N2 into IA2, which gave us this value N2 into IA2 is equal to 30,000. Now, from the second condition, which is torque is directly proportional to speed square, and further we equated it equal to phi2 by phi1 into IA2 by IA1, which gave us this IA2 by N2, and if you further go ahead 50 by 3, so this value is different. Now, if we multiply it, we will get IA2 square, isn't it? If we multiply this expression, this is second expression, and this is first expression. Let's suppose and remove all other firsts. So this one equation and this second equation, from these two equations, if we multiply, we will be able to write IA2 by N2 into IA2 into N2 is equal to root 2 into 50 by 3 into 30,000. Is it fine here now, or I can clarify it once more?
So is it fine, sir? Wouldn't it be easy if we substitute IA2 by 30,000 by N2?
IA2 is equal to 30,000 by, that is another way. Yeah. Here also you can substitute directly 30,000 by N2. Yeah. It will be much easier. Yeah, you are right. So 30,000 by N2 square is equal to root 2 into 500 by 30.
Yes, sir.
Yeah. So it will be N2 square is equal to 3 3s are 9 into 10 raised to power 5 divided by 500 into root 2. Okay. So if you under root it, it will give you N2. So let me calculate it.
35.67.
35.67. Yeah. So 35.67.
ये तो बहुत
That's
बहुत कम हो गया.
yeah. So some mistake have we done? Did we substitute here correctly? IA2 N2 was 30,000. Okay. And
Sir, I have one idea, sir.
yeah.
Sir, here the question, there is never stated that torque is changing, sir. Only change is that we have changed the arrangement of field coils.
Mm-hmm.
So then
Yes.
let us assume that the torque is same and use
Mm-hmm.
the torque equation K phi n.
K5 IA.
Uh, sir, no, sir.
Okay. See,
Sir,
just
sir,
let
sir,
it.
one more
Huh.
thing. EB is also same, sir.
EB is same. Yeah. So from this
Yes, sir.
condition,
Sir.
we ended up with 30,000 value, right? Why it is not zooming out? Yeah. So from EB is equal to 1, means EB2 by EB1 is equal to 1. We ended up with IA2 into N2 is equal to 30,000. And when torque is proportional to N1 by N2 square, means a speed square, we got this expression I2 by N2, I2 by N2 is equal to root 2 into 500 by 30. So I think here we have done this mistake. Let IA2 by IA1. Let me rearrange this particular thing. IA2 by IA1 is nothing but root 2 into N2 by N1. Now IA2 by N2 is equal to root 2 into IA1, which was 30, divided by N1, which is 500. Okay, so now we just go ahead with this and let us see what it will prove. If again it will give the same, then we have to think a new approach. We will multiply both the expressions. Okay, so which will become IA2 square is equal to root 2 into 30 by 500 into 30,000. Okay, so far so good, I guess. We are not committing any mistake. We have to double check. IA2 by N2 is equal to root 2 into 30 divided by 500. Yes. Sorry, could you please repeat?
50.45.
IA2 is how much? 16.45.
50.45 he said.
50.
Yeah, 50.45. Now we can plug in here this value of IA2 in any expression, right? We know all things. We just need to find out the N2. Okay. So N2 is equal to N1 into IA2 by IA1 into 1 by root 2, which will be equal to N1 is 500, IA2 we have calculated 50.45, IA1 is 30. Now we will have higher speed, I guess. So it is equal to 500 into 50.45 divided by 30 into 1 by root 2. It will give you 594.55 RPM. So I think we did some numerator denominator mistake in earlier part where we just plugged in here. So just you go back after this session and verify it. Okay.
Sir,
Yeah.
I have one more idea, sir.
Yeah, please tell.
Sir, we are not changing the terminal voltage, sir.
Mm-hmm.
Therefore, back EMF in both the cases will be same, sir.
Yes.
Then K phi 1 N1 will be equal to K phi 2 N2.
K phi 1 N1 is equal to K phi 2 N2. Yes.
K will be cancelled.
So phi 1 N1 is equal to phi 2 N2.
And we will move phi 2 from right to left hand side, sir. Phi 1 by phi
Mm-hmm.
2, we know that it is 2, sir.
Phi 1 by phi 2 we know 2. That you cannot say directly, isn't it? Because in
Sir,
second case, IA2 is not equal to IA1. From this circuit, if you see, in this circuit, IA2 by 2, it is not equal to IA1, which we're showing here. And field current is equal to armature current in both the cases. What do you think?
sir, the load is not changing, then IA should remain the same, sir.
Load is not changing.
So the torque demand is
Load,
not changing, sir.
no, load is changing. No, see, torque is proportional to square of the speed. It means when we have to find out at all the conditions at the new speed, at that time your torque will be changed. That is proportional to the square of the speed. Your terminal voltage is same because of the negligible losses, but your torque is changing.
Okay. Speed will change, then torque will change.
Torque will change from the this given problem condition as well as from the characteristics of DC machine. If you derive, then you will also find. So torque will change, and hence your
Okay, sir.
current will change, and that's why we cannot go that road. But anyway, it's good to think that, but verify that what will happen. the only bottleneck in DC machines problem that you change one thing, particularly in DC series machine, everything is connected to each other, and uh, that's what we have been struggling with. That one thing we are changing, another thing is already changed, and it is becoming difficult. So that's the only difficulty in this kind of question. But if you are conscious enough, you like everyone has to pay attention in the exam questions so that we do not commit any mistake. Otherwise, only three equations are there in this machine, right? Torque is equal to K phi Ia, and back EMF is equal to K phi omega, and 1 kVL Kc. But only with these three expressions, we can derive so many things, and we can make so many manipulations. Okay, then shall we move to the next problem?
Yes, sir.
Okay, great. Okay, so here we will be inserting an external resistance in the series to find out. First thing, we need to find out the speed and current. So basically, we need to find out the case when we are inserting 4.6 ohm of additional resistor Ia2 and N2. Okay, so again, this is series motor with total resistance armature plus field is 0.4 ohm. It was taking 40 amps of current and driving a load at 600 rpm. Torque, load torque is proportional to square of speed. Now we have to find when additional 4.6 ohm of resistance is connected in series. So basically R1 is 0.4 ohm and R2 is 4.6 plus 0.4, which will be equal to 5 ohm. Now again, to find the speed, we must be aware of back EMF for both the conditions. So EB1 will be equal to 250 minus 40 into 0.4. So it will be 236 volt. Now what will happen to EB2? EB2 will be equal to 250 minus Ia2 into 5. Okay, we don't know Ia2 because, of course, your torque has been changed, so current will also be changed. And in this case, we have added additional resistor as well, so that will completely change the scenario. So for calculation of Ia2, T2 by T1 is equal to N2 by N1 square. Okay, is equal to Ia2 by Ia1 square, because If2 is equal to If1. So from this condition, we will end up with N2 square by Ia2 square is equal to N1 square is how much? 500, I guess. 600. 600 square. Ia1 square is 40, so 40 square. So if you find this ratio N2 by Ia2, it will be 600 by 40. So it will be 15. This is our first condition. Now second condition is what? Second condition is we are applying, back EMF. So from back EMF ratio, we can try to find out the speed. So EB2 by EB1 is equal to Ia2 by Ia1 into N2 by N1. Now I am directly using at the place of phi Ia2, I armature current at the place of flux, and straight away using armature current. I hope it should not create any problem or confusion. So if you find out EB2, we have already found EB1 will be EB1 equation is this. Sorry, EB1 is 236, EB2 is this. So EB2 is how much? 250 minus 5 Ia2. EB1 is 236 is equal to Ia2. Ia1 was 40 into into and N1 is 600. So from this expression, 250 minus 5 Ia2 into 6 for the 24,000 is equal to N2 Ia2 into 236. So first we should try to divide. If it is divisible by 236, 24,000 divided by 236, it is approximately 101.7. So anyway, 250 minus 5 Ia2 is equal to, we want to find the current, right? So we should change the relationship from this N2 by Ia2 is equal to 15. So N2 is equal to 15 Ia2, we can write it. So 15 Ia2 square into 236 divided by 24,000. Okay, so I think we will end up with one quadratic equation, Ia2 square into 236 15 24 divided by 15. So it is 6.8. This whole component is 6.8. Let me circle it. It is equal to 1 by 6.8. So if we multiply it into 5, it will be 33.9 plus 33.9 Ia2 minus 250 into 6.8. It will be 1700 is equal to 0. So this is your quadratic equation. It will give you two solutions. Okay, so Ia2 square, if you solve on the calculator, how much you are getting? We are getting two solutions. Ia2 is equal to, from the calculator, if you solve, 27.63 amps, and other is minus 61.52 amps. So of course, minus 61.52 doesn't make sense here. So 27.63 amps will be correct answer. I hope you also got the same answer, right?
Hello.
Hello.
Sir, I am getting in complex form.
Have you put the correct numbers in your calculator? So see, to get the complex form, your component must be negative. So let me solve it from the conventional way. If you get Ia2 is equal to minus b 33.9 plus minus 33.9 square minus 4 into 1700. So if this 33.9 square is higher than that value, then you will get the complex number. So let me check it. 33.9 square. Yeah, it is higher than. How come? But calculator provided something else. Oh, okay. No. So see, this minus 4AC will be plus, no? This minus and this minus will be plus, right? Divided by 2. Did you get, where did you commit mistake? Minus 4 into 1 into minus 1700. Are you able to figure it out? So if this whole component is negative, then only you will get complex terms.
Okay.
You got the point, right, Neeraj?
Yes, sir.
Yeah. So are you able to get this 27.63 amps?
No, sir, I was not calculating.
Okay. Anyway, so if you calculate, you will get the similar value. Now N2 by IA2, we know N2 by IA2 is 15. So N2 by IA2 is 15. So
Sir,
N2 is equal to 50. Yeah.
sir, please show this equation 250 minus 5 IA2 by 236. This
Hmm.
above
Yes. Hmm.
is this
Yeah.
equation.
Hmm. Which one? This one.
Yes, sir. Sir, in this above equation 250 minus 5 IA2 by 236 equal to IA2.
See, the coefficient of IA2 square I want to eliminate. Okay. So what should we do? We should divide it by the same coefficient on both sides. This 236 into 15 divided by 24,000 will be equal to 1 by 6.8. So this 1.6.8, it is nothing but IA2 square divided by 6.8. So we multiplied on the left side with 6.8.
Sir, I did correct, but why I am getting wrong? I did not able to understand.
You calculated some calculator. You got this equation or not? This equation.
No, sir. Actually, what I did, I directly place N2 is equal to 15 IA
Mm-hmm.
and then make equation and put in a calculator that is giving complex form the value of IA2.
Okay, maybe you might have plugged in this as plus 1700. If you plug in minus 1700, then you might get correct. That's one possible mistake you can commit. Otherwise, you re-verify your calculation. Okay.
Okay, sir.
Okay, because there is no point of getting complex conjugate because that will make completely AC current, which is not possible in DC machine, right?
Sir, I have also got 27.625 and minus 61.52.
Yeah, it means if we two are getting this, then it's highly probable that you might have committed mistake, Deepak. So you re-verify it. Okay. So now N2 will be 15 into 27.63, which will give us 27.63 into 15. It is 414 RPM, 414.45. So at this speed, the machine will operate when you provide additional resistance in series. Okay. Any final doubt in this particular problem?
नो सर, इसमें ठीक है, इससे पिछले वाले को दोबारा देखना पड़ेगा.
Okay, so just after the lecture, you go back and see, or if still there is any problem, then next week फिर से इसको we will revisit, right?
ओके सर.
Okay. So basically, हाँ यहाँ पे like what we did, we got confused here. Like IA2 by N2, we plugged in some some confusion might have arrived there, but anyway, after the calculation, you can get. Okay, so one problem I wanted to discuss based on losses, which arrived in one lecture. So losses are very important in DC machine because uh, at what node which losses will be there, to identify that particular thing is a bit tricky in DC machine. So let us see one problem based on losses. Okay, so here we need to find out the full load output. Okay, so full load output along with some other parameters we will discuss. So let us try to find out. I hope you are able to see the problem.
Yes.
Yeah. So this is a DC shunt motor again. We are done with the series motor. So with DC shunt motor, we have armature resistance and field resistance given. It takes 5 ampere at no load condition. At full load, it takes 26 amps. We have to find out the full load output, power output at full load. So first we should segregate the field current out of it. So field current will be how much? 230 by 231 amps. In any case, it will be constant unless we are providing any additional resistances. Now, at no load, armature current is how much? 5 minus 1. Can I write? 4 amps.
Yes, sir. 4.
4. So total no load losses will be how much? Total no load losses.
920.
920 how? 4 the square into, you are doing 4 the square into what? 0.6. That's what you are doing or what? See, total no load losses will be what? At
So
no
terminal
load,
voltage into
whatever,
current.
yeah, terminal voltage into line current. Whatever you are feeding into the motor, all are going at losses because you are not applying any load. So VT into IL, no load. So VT is 230 volt into IL no load is 5 amps. So it will be 230 into 5, 1150 volt. Now you can segregate from this 1150 watt, sorry, watt, 1150 watt, how much will be field copper loss, how much will be no load armature copper loss, and after reducing field copper loss, no load armature copper loss, the remaining losses will be your rotational losses.
Yes,
So
rotational and core losses.
yeah, rotational and core losses. So all magnetic and mechanical losses you can say. So rotational and core losses will be how much? 1150 minus 4 square into RA was 0.6 minus 1 square into 230.
230.
Exactly. So it will be 1150 minus 16 is 1.6 into 6, it is 9.6 minus 230. So it will be 1150 minus 230 minus 9.6. It is 910.4 volt. So it is your no load rotational losses. But it will be your rotational losses. Okay. So, and if let us see in that manner, what is no load rotational losses? So at no load, EB will be how much? EB will be 230 minus 4 into 0.6.
Sir,
Yeah,
they did not given field resistance.
they have provided 230 ohm. 230 ohm.
Okay, sir.
Okay. So 2.4 to 27.6. So why I am trying to calculate EV at no load? Because whatever you have this hard way, if you are not given any losses and all, so what you should do to calculate no load magnetic as well as mechanical, means core loss and rotational losses, what you should do, EV at no load into IA at no load. Okay, so this expression also give you rotational and core loss. Yes, so it is very useful in some examination if you want to quickly figure out how much rotational and core losses, you just multiply this expression. So anyway, your armature is rotating. So whatever current in your armature going at no load, that losses, that it is what V into I, voltage into current. So that back EMF into no load current will provide you the rotational and core losses. So if you try to find out EB into no load, so EB no load we have calculated 226.6 into IA no load is how much? 4 amps, right? If you calculate it, you will get 910.4 watt. Okay, and now you add on top of copper losses, field copper losses, and all, so you will get those total losses. Okay, so we need to find the output. For output, we can what we can do full load for full load output. For full load output, you have to calculate input minus losses. So output is equal to input minus losses. So input is how much at full load? 230 into 25, right? Because at full load motor is taking 26 amps. 1 amp is going in field. So remaining 25 amps will go in armature, right? Minus this rotational losses and core losses 910.4 minus at this current 25 amps of armature current in 2.6 of armature resistance. That will be armature copper loss.
Yes, sir.
But this rotational loss will be fixed until the rotational speed is changing. Okay. So because if your speed will change, your EB will change, right? So hence this rotational losses will be constant. It is a function of a speed or frequency. Rotational loss plus core loss. Both are function of frequency. Rotational loss as well as core loss, both are function of frequency. As you change your speed, both will change. Minus field loss, that is 1 square into 230. So this whole calculation will give you your full load output. Let me calculate it. 230 into 25, it will be 5750 minus 910.4 minus 25 square into 0.6, it is 375 minus 230. So 5750 minus 9 10.4 minus 375 minus 230. So it is coming out to be approximately 4234.6 watt. Are you getting the same?
Sir, I have one problem, sir.
Yeah.
Sir, while calculating power input, we have 230 multiplied by 25. We
Hmm.
ignored the part going to the
Acha.
field.
Yes, 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 yes. Yeah, yeah. You have pointed correctly. Yeah, that 26 will be here, not 25. 25 we have used here for armature copper loss, but that will not be everywhere. So this armature copper loss is 25 fine, but here it will be 26. So now it will change to 230 into 26, 5980. The rest everything is fine. So now this value will be plus 230. So how much we calculated? 5. What was the last value? 4234. 4234.6 plus 230. It is 4464.6. Yeah, thanks Neil for pointing this out. So it is 4464.6. Okay, so it is the output power at full load. Now
Hello,
is it
sir.
fine? Yeah,
Sir, we can write here 25 if we can, if we did not write this 1 square into 230,
yeah,
then
yeah,
we can write
definitely.
25.
There are many ways to manipulate. You could have eliminated it and you could have written 25. That is also fine. So basically, you
Okay,
should
sir.
consider that field loss is counted as one. Okay. If you are integrating field losses in input, it means you should remove it from calculating separate loss. Otherwise, it will create double field losses and we will have less output as we have 4244 something. So that was it minus 230 volt. Earlier we calculated this value minus 230 volt. So we counted field losses twice. That's we should avoid. Okay, then. So the next thing is you could easily find out the efficiency, right? P out minus P in by into 100 equal to 4464.6 divided by input was 5980. So it will be how much? It will be approximately 74% or 75%. So this much. Okay, so I hope you got good idea of how to compute losses in DC machine. Okay, particularly how to calculate this rotational loss and core loss, because it is very important from gate type of examination. They frequently test this concept. So, or anyway, it will be useful for this exam also. You will have this NPTEL examination, so you will be asked such questions. Okay, then. So this is all for this week. Uh, Next
Sir,
week
I have
will
one
be.
question, sir.
Yeah, yeah. Go ahead.
Sir, can you suggest any book for electrical materials?
Electrical materials. I think Chapman book is good from that perspective. Uh,
Okay.
Chapman book should be good. Let me see once.
Electrical engineering materials.
Yeah, he is
Yes.
asking about materials. So for magnetic circuits, or you can refer this DP Kothari book. That should also be provided with some materials.
Okay, sir.
So in DP Kothari, I am sure that it is given. that one topic as magnetic materials and their properties. But in Chapman, you will get good questions based on magnetic equivalent circuit. So you see both the books. Uh, I think you will find enough content on materials.
Okay, sir.
Okay, then thank you very much for joining. So we should wind up now, and next week will be our last week. So see you next week.
Okay, sir. Good night, sir.
Good night.
Thank you, sir.
Thank you very much. Good night.